Okay, hello, I'm Samothy. I'm going to talk to you about regular expressions. There is a bunch of maths in this talk, there's a bunch of graphs. Hopefully, if you know what a regular expression is, then this talk will be completely fine for you. As David said, if you want to ask me questions, I'm probably going to have to do that later in the conference because there's a lot to cover and I'm not sure I'll have enough time to answer questions. So my details are on the screen, also the link to the IPython notebook. This is the first time that I'm doing a talk with a Jupyter notebook, so had a lot of trouble with getting the slides to work. Hopefully it looks okay. Sorry, the font's a bit small. Let's get started. So, regular expressions. What is a regular expression? What do they do? They are a bit of a garbled collection of just random characters that you smush together with a few, full stops and a bracket here and there, and hey, it matches a string! And it goes, yes, this string is one I recognize. If you wrote the regular expression right, which you probably didn't the first time, and then you stuck it into a thing online, and the thing online told you that you need to put a minus the \w here, and plus this there, and more brackets. But where can we find regexes? All over the place, really. We see them everywhere that you need string matching. So maybe that's in a compiler. Maybe they're matching members of strings in the language, in the programming language. Maybe we see them in web servers. You probably need to know that the string you received is a URL that you are aware of and you know how to handle, or maybe you want to know whether the string that you received includes the subdomain that you're interested in serving a web page for. But essentially, we see regular expressions in pretty much any program that needs to know if a string is a certain kind of string, or if that string belongs to a certain class or a certain language of strings that we're interested in. So let's get on to looking at one of these regular expressions. This regular expression is terrible. It works, and I'm using this as an example because it is short, and it matches a string that you'll all be aware of, that you'll all have seen before. It's got an @ symbol in there and a full stop. Can anyone hazard a guess at what this might match? Emails. Right. So, yeah, it's not a very good email matching regular expression. It starts off by saying any characters, those, we're looking at those, yes, those ones, followed by an @ symbol, yep, interested in that, followed by any characters, any number of those, however many, followed by a full stop, followed by some more characters. So it does actually work. Like, if you pass it some email address like things, then it does match them, and it goes, yeah, these are members of our language of email addresses. But it's not very good, but it works. So we can also express this regular expression, not like this, but in a bit of a different way. You might not have seen a regular expression expressed as before. We can express it as an automata. This is some code that I wrote that uses a little library, little class that I wrote, and it makes automatas that look like that. Let's just have a look at this for a sec. So we've got our regular expression, and it looks like this. We've got our any characters at the top, and we spin around, matching any characters until we see an @ symbol. And then we move on to the next state, and we match any characters, and we spin around on that until we see a full stop. And then when we see a full stop, we continue on to the next state, which matches any number of characters, continues to the last state, and spins around on that until we reach the end of the string. And this last state here has a dashed lines on it, which indicates that when we reach the end of the string and we're in that last D state at the bottom there, we can accept the string. This graph can also look like this, which is some maths. It's got a bit of set theory stuff in there. That's a formal definition of a finite automata. You probably don't need to think about this kind of thing too much, but I'm using some of the mathematical representations a bit later in my talk. So altogether, that's what they look like. Oh no, I'm good. Did I need another one? So finite automata. That graph that I showed you is a finite automata or a state machine. It is a set of states, and it's got some transitions between the states. Given that we have a certain criteria that we can meet, if we meet that criteria, and that criteria is on a transition, we can go from one state to another state, from the start to the finish of the finite automata. Finite automata are capable of recognizing regular languages. Regular languages can be represented using regular expressions, or they can be represented using finite automata. So I'm just going to go over some terms here before I get into talking about designing finite automata and representing regular expressions using them. First off is a set. It's a Python set. Everyone's used a set in Python, so you'll all be aware of what that is. A collection of items where no item appears more than once. A language is a set of strings that can be recognized by a machine. A string is a combination of symbols, such that each character in the string, each symbol in the string, is a member of the alphabet that we're using. And an alphabet is a finite set of symbols. So going over those all together, if we look at the start at the bottom here, we've got an alphabet, which is a set of symbols, a string, which is a set of symbols, but like together in a string, such that every character or symbol in that string is a member of the alphabet. And the language is just a set of strings. So really they're just a few sets. The empty string is a bit interesting. The empty string represented by this little E-like character here. I think it's epsilon. It is epsilon. Yeah, you know, these are just math symbols. A string containing no characters. Here we treat it, with finite state machines, we sort of treat it like a zero character, like a nothing. I mean, there's quite an important definition between a nothing and a zero. But here we treat it like a nothing kind of character. And we've also got the empty set, which is a set containing nothing, but the set still exists. So it's a set with nothing in it. It's like a box with nothing in it, but the box is still a box, right? So go back to regular languages. Regular languages, so those are sets of strings. A language is regular as long as some automaton recognizes it. If you can make an automaton that recognizes this language that you've got, that language is a regular one. So let's recognize a string with the symbols 0 and 1 anywhere in that string. There we go. Yep, there's the maths. That's it. We're already going to show that. Nobody needs to see the nice pretty graph to understand what that means, right? Right. Well, it's a bit clearer if I display it as some code here. So Q equals A and B and C is the set of states in our graph, in our state machine. The alphabet, so the possible characters, is represented by the sigma symbol, and the possible characters that we're looking at is a 0 or 1. So our strings only ever contain zeros or ones. The start state, the first state in our graph, in our state machine, is the A state. And the end state is a set of possible states. We can have many end states, but we've only got one here, and it's the C state. So let's create our automata. It's called 0, 1a. And we'll show you the automata along with all the edges that we create to transition between the states. If you'll note up here, I'm using the example string 001, 00. That does contain the substring that we're looking for, 01. So let's walk through the automata. We start in state A, and we put in our first character. And we go, what is that character? Is it a 1 or a 0? It's a 1. If it were to be a 1, we would rotate around and stay in the A state. If the character that we've got were to be a 0, which it is in our case, our string is 0, 0, 1, 0, 0, then we would transition from our A state to the B state. And then we look at our next character. Is it a 0 or is it a 1? It's a 0. So we spin around and we go straight back into the B state and we read the next character. So we've read 2 characters out of our string. Our next character is a 1. Our string is 0, 0, 1, 0, 0. And because our next character is a 1, we transition down to the C state. And now what we've done is we have seen the substring 0 and 1. And those are the characters that we are looking for in order 0, then 1. And because we've seen that substring, we can finish as soon as we see the end of the string. We don't care about any other characters as long as they're 0s and 1s. We don't care what order they're in. We have seen the substring we're looking for, and we can finish, complete, and tell the user that string is a member of the language that we are looking for to recognize. So, moving on to more interesting automata. What we just looked at is a deterministic finite automata. Deterministic means that for every state, there is one transition for every symbol in the alphabet. Our alphabet was 1 and 0, and so for every state, there was a transition to a different state, even if that state is the same state. Let's probably go back and I'll explain that a bit better. Right, so for every state, there is one transition and only one transition for every symbol in the language, 1 and 0. That makes it a deterministic finite automaton. We're going to look at non-deterministic finite automaton in the effort to move on a bit towards our regular expressions. So we're going to look at another automaton, and this automaton has got a few more states. It's got A, B, C, and D. It's got the same alphabet, 0 and 1. The end states is just D. We've only got one end state. And it's got some other edges, some other transitions. And it looks like this. This time, we're going to recognize strings that contain 1, 1, 0 as a substring. And we're going to use the example string 0, 0, 1, 0, 0. Because that does indeed contain, it doesn't. What have I done? I was silly. Never mind. We'll look at a different substring, and I've just come up with one off the top of my head. I'm clever like that. So this is our non-deterministic finite automaton. Let's look at the example string 0, 1, 1, 0, 0. So we've just got 2 1s in there instead of 1, 1. The important thing to notice about this automata is the fact that the first state, the A state, has got a transition for the 1 symbol, and it's also got another transition for the 1 symbol, and that's really important. It's got 2 transitions for the same symbol. So let's walk through this. If we've got a 0 as our first character, we step into the finite automata, we look at the A state, and because it's a 0, we just transition around and stay in the A state. The next character is a 1. 0, 1, 1, 0, 0. So the next character is a 1. And this is the really, really interesting part about non-deterministic finite automata. They're a bit like threads in your computer systems. You can have two automata, or one automata that's in two states at the same time. Or you can also think of it as if you were forking a program. So you've had the same input into your program, and you split it, you've got the same program running concurrently twice. And this allows you to process much more complicated things. And we'll talk a bit more about that later, but let's stick on this for now. So if you imagine in your brain boxes, we've got our state A, and we're currently in state A, and we're just about to read another 1 from our string. So we read it, and we simultaneously transition to the B state while also transitioning around in the A state. And the reason we do this is because the following character after the character we've just read may well be a character that we can transition out of the B state with, or it might be one that we need to stick here and stay here again, right? This will become clear in a bit. So, with our string 0, 1, 1, 0, 0, we now read another 1. So we are simultaneously transitioning into the C state while also still being in the A state and spinning around on that once again. Our final character in the string is a 0, so we transition from C into the D state while still being in the A state. If we wanted to, we could add a spinning thing on the end of the D state here to say if you've got any more extra characters at the end of the string, stay there. But the beauty of non-deterministic finite automata is that we're still in the A state. Every time we read a character, we keep transitioning and we keep going, this is the 1. This is the character that starts our substring. This is the one that's going to take us to the final state. And then if we get to the D state and there's another character after that, it doesn't matter, because we are simultaneously in the A state still. So it's a little bit difficult to explain, and I hope that I'm getting this across, right? But like I said, it's like having forks. Every time you read a character from your string, you fork your automata in the locations that you can fork it. In this case, we've only got A. And that means that you can explore paths towards your final states while simultaneously not exploring them and staying in other states. So like I said, it's about being able to express more complicated computational problems using non-deterministic finite automatons than you would be able to represent using a deterministic finite automaton. They are both equal. An NFA and a DFA can perform the same computations, but an NFA can do it in much less space because you can explore multiple paths at the same time. So for the remainder of this talk, I'm going to be representing things using non-deterministic finite automata, because things get a little bit complicated when you're dealing with regular expressions and expressing those as automatas. So combining the automaton, this is important and fun. We've got a couple of operations. The union operation, we can stick automatas and go, hey, if we get a string, I want to recognize two substrings in that string, but it's an inclusive OR. So I want to recognize either this or the other one or both. So yeah, it looks like this with a little U symbol, a little cup symbol. We can create automatas, and we can create one automata that recognizes the substring 110 here. And we can create a second automata that recognizes the substring 111. And we can combine those and go, when we start here, at the front, we transition to both A1 and A0 simultaneously, execute the automata, and we can decide whether we've got either or both the substrings 110 and 111. We've got another character in there which you've seen before, the Epsilon character, the empty string. Here we're using it to say if you see an empty string, just transition whatever character you've got. If you've got a 1 or a 0, doesn't matter, just run either of these things. So, yeah, the empty string, start there, do both of those. We can be in both A1 and A0 at the same time because it's non-deterministic. Yep, so concatenation, a logical AND. So concatenation, if we've got two substrings, we want to recognize both of them, but we want to check to see if they are both in the string at the same time. So one substring followed by another one. We can stick, it's like that, it's a little O. We can stick our automata together, like literally glue them together, 110, don't finish there, but carry on recognizing the second substring, and if we see the second substring, finish at the end there. So we just shove them both together. The star operator is essentially more of that, so just keep recognizing this one, so we can have a substring however many times you want. It looks like a star. I'm sort of running out of time. So the star operator essentially just adds one extra transition state here that says if you got to the end, just go right back to the start and carry on forever until you reach the end of the string. So now we're back to regular expressions. I'm aware that we're running out of time. Do we have a break after this?
We can have a break afterwards, so if you're a couple minutes afterwards.
If you feel like leaving because you really want to go get a coffee, do that. I probably will run over. Just warning, I won't sue you. So regular expressions, they describe a regular language, just like our finite automata. And we can make a regular expression that looks a bit like this. It doesn't look like a regular expression that you've seen, right? It doesn't look like one you've defined in Python. But it's a regular expression. We can read this as, I'm looking for a string that starts with 0 or a 1 any number of times, followed by 110 or 111, followed by 0 or 1 any number of times. That sounds like a regular expression. Those 1s and 0s could be A, B, C, any character. They could be any other symbol that we might want to represent in our system. And that is essentially what a regular expression is, right? It's a regular language. But this is a bit of a mathsy way of expressing it, and it's a bit in line with the finite automatons that I was talking about earlier. So, what's that doing there? Oh yeah, right, okay. So, we had our finite automaton that recognizes 1110 and 1111, which is the middle section of our regular expression here. But we also need to recognize 1 or 0 any number of times. And we can do that. We can go, here's a regular expression that recognizes zeros. Here's an automata that recognizes zeros. Here's an automata that recognizes 1s. Here we can go 1 or a 0. 1 or a 0, either of those are final states. And we can condense that into one finite automata, because the final automata at the end of this talk is very big, so I condensed it a little bit. But we can star that, and we can say, okay, 1 or a 0 any number of times. So that's the first bit of our regular expression. We got 1 or 0 any number of times. Then we got the second bit, the 111 or the 110. So Yeah, here's our 110. Here's our 110. 111. That's not correct. That's not correct either. Okay, well this is the wrong one. Okay, so we can have our...
It's like a regular expression.
Yeah, right, so it's a regular expression, it's broken. That's what they do. Right, so this regular expression would recognize 110, and then it would finish. And we can union those and say we want to recognize 110 or 110 in this case because I broke it. And we can combine those with our 0 or a 1 regular expression at the front, followed by 110 or 110, followed by 0 or 1 any number of times, and this is our regular expression from earlier, except we represented it as a graph instead of representing it as a few characters on a screen. Oh, so let's do an email. Right, this one gets really big. It's exciting. There's our regular expression from earlier, which recognizes an email. Any characters followed by an @ symbol, any characters followed by a dot, followed by any characters. So our alphabet, for conciseness, is A, B, C, D, @ and full stop. Because who needs more characters than A, B, C, D in your... You've got vowel and 3 consonants. Okay, so we're going to start by recognizing any characters, and then we're going to finish. Any of those characters, not including the @ symbol, because no, you can't have @ symbols in your name. And we want to star that. We want to say any characters, any number of times. And we want to follow that by recognizing an @ symbol. And what is that? Then we want to stick them together alongside... Oh yes, that one's recognizing the dot. You can just see it there. There we go. Right, so this one recognizes a full stop. And then we can stick them together and recognize any characters, followed by an @ symbol, followed by any characters, followed by a full stop, followed by any characters at the end. And there it was to try and make it a bit bigger. I'm done! Woo! Okay, quick recap. Finite automatas are simple state machines. Deterministic finite automata and non-deterministic finite automata recognize regular languages. They're all equivalent in power. Regular language, a regular expression describes a regular language. And regular expressions can be drawn as finite automata, and you can think about them as graphs, like how I expressed them to you there. Further reading, if you want to. Generalized NFAs is a method of converting a deterministic finite automata into a regular expression. So we're going the opposite way to the one I showed you here, which was going from regular expression into a finite automata. And a fantastic book, which I highly recommend, Introduction to the Theory of Computation. It's very, very good if you are at all interested in finite automata, regular expressions, regular languages, non-regular languages, lemmas, all of this theory of computation stuff. Very good, very easy to understand. Whew. Okay, that's me. I have done a talk for you. Thank you very much. If you want to ask me questions, you can catch me outside.